In this video, we will discuss the formation of energy bands in solid. Quantum mechanics states that electrons in an atom can have one of these energies in a set of discrete allowed energy levels. So, for example, if you look at the energy level scheme shown in the left for hydrogen atom, the ground state is located at 13.6 electron volt below the free electron energy level, and you can see these higher excited states. And if the electron is fully liberated from the proton, then they will reach the energy levels of free electron. These individual energy levels are called the atomic energy levels, and the wave function corresponding to each of these states are called the atomic orbitals. Now let's consider the formation of molecule. If you bring two hydrogen atoms close together, then the electrons will begin to feel the presence of the other proton, and this interaction results in the splitting of energy level. So as shown here in this top left figure, the ground state energy level of hydrogen atom here and hydrogen atom here, when they are brought close together, they will form two new energy levels, and one has a lower energy and the other has higher energy. The lower energy state is called the bonding energy level or bonding molecular orbital. Higher energy state is called the anti-bonding state or anti-bonding molecular orbital. The hydrogen atom has one electron each. So when you form H2 molecule, there are a total of 2 electrons, and electrons like to occupy the lowest possible energy state. So both of these 2 electrons come to occupy the bonding orbital. So if you compare the energy of the atomic hydrogen here or here and the energy of the H2 molecule, you can see the electronic energy is lower in H2 molecule. In other words, formation of H2 molecule is energetically favored, and hydrogen like to form molecule. On the other hand, if you look at the next biggest atom, helium has 2 electrons each. So when you bring 2 helium atoms close together, you will form bonding orbital and anti-bonding orbital, but there are 4 electrons total, and Pauli's exclusion principle prohibits that more than 2 electrons occupy the same energy level. So you can only have 2 electrons in the lower energy bonding state, and the other 2 has to go to the higher energy anti-bonding orbital. So if you compare the electron energy of the helium atom and helium molecule, there is really no energy gain, and therefore helium likes to stay in atomic state. So if you purchase helium gas or the balloon filled with helium gas, what you actually get is not a molecular gas of helium, but it is an atomic gas of helium. Now we can imagine that we can continue this exercise. So bring in 3 hydrogen atoms together, 4 hydrogen atoms together, 5 atoms together. When you do that, then these energy level splitting will continue. When you have 2 hydrogen atoms close together, they interact, produce 2 energy levels, one lower energy, one higher energy. When you bring 3 hydrogen atoms close together, then it will create 3 different energy levels. 4 hydrogen atoms close together will produce 4 different electronic energy levels. Now, if you continue this to 10 to the 22, 10 to the 23, 10 to the 24 atoms close together to form solid, you will produce 10 to the 22, 23, 24 different energy levels. And this is schematically shown here. So in this case, we show the case of lithium atom, which has 3 electrons, and the 2 electrons is in the lowest energy state, we call this a core electron. And the third electron, due to the Pauli's exclusion principle once again, has to go to the next high energy level. And this highest energy electron in an atom is called the valence electron, and these are the electrons that participate in chemical bonding. So when you bring the lithium atoms close together, then these atomic energy level once again will begin to split. In this figure, in this graph, the x-axis represents the distance between the neighboring lithium atom. So when they're infinitely far away, as shown here, this is the atomic lithium energy level. When you bring lithium atoms, multiple lithium atoms close together, then you go into this direction in your x-axis, and as you do that, the energy level will begin to split. And there will be the total number of energy levels here in the scheme will be equal to the number of lithium atoms, which is very, very large. So you can imagine there will be very, very large number of energy levels in a relatively short, relatively small range of energy. So for all practical purpose, in this case, instead of considering this as a discrete energy level, a set of discrete energy levels, for all practical purpose, we can treat this as a continuous range of energy that is allowed. And that range of energy that electrons can possess continuously allowed range of energy is called energy band. So this is the energy band right here. And now the number of electrons in the lithium solid will be equal to the number of electrons that each lithium atom provides, which is 1 in this case, the only one valence electron. So now these electrons will be piling up from the lowest possible energy state, and in this case you can imagine that the electrons will fill up the energy band exactly halfway. So you have a continuous range of energy that is allowed. We call that energy band. So in solid, instead of a discrete energy level, we have energy band. In the case of lithium, you have an energy band that is partially filled. Electrons fill up the band from the bottom to roughly midway. This is a very important characteristic I will highlight again in the next video. Now let's consider silicon. In the case of silicon, there are 4 valence electrons. Silicon is a group 4 element, so there are 4 valence electrons. And if you look at the energy level scheme of a silicon atom, the valence electron is distributed over 2 separate energy levels. Okay? This is 3s, this is 3p. And as you bring silicon atoms, multiple silicon atoms close together, then these 2 energy levels will split again, just like that. Now, because there are 2 energy levels splitting and overlapping, they will end up producing 2 energy bands here, 1 lower band and 2 higher band, separated by a region of energy that is not allowed. Okay? So the lower region of energy that is allowed, we call that valence band. A higher region of energy that is allowed, we call that conduction band. In between, there is a region of energy that is prohibited. Electrons are not allowed to possess this energy. We call that energy band gap. So, in a very typical energy band diagram of a semiconductor, you have a higher energy region that is allowed. Electron can be here. We call that conduction band. Lower region of energy that is allowed, we call that valence band. In between conduction and valence band, there is a region of energy that is not allowed. We call that energy band gap or forbidden band gap.